Log on, tune in, find out. Another good idea from Cambridge.
First talk this afternoon, we're very grateful to Terry Tao for finding the time to tell us about the polynomial method in combinatorial incidence geometry.
Okay, well, thank you. So I was asked to give a talk to an algebraic geometry audience, and I don't work in algebraic geometry, so it was a bit of a challenge. So I'll talk about a field I do work in, which is combinatorial incidence geometry, and how methods from algebraic geometry have been used in recent years to make a lot of progress on many of the outstanding problems in the field. So far, we've been using fairly basic methods in algebraic geometry. I mean, things like Bezout's theorem or the classification of rolled surfaces. So from almost 19th century type algebraic geometry. But it's conceivable that to make further progress using this method, we'll have to use more advanced methods in algebraic geometry. So let me tell you what combinatorial incidence geometry is. So combinatorial incidence geometry is the combinatorial study of configurations of simple geometric objects. Really simple objects like points, lines, planes, circles, and so forth. So you have maybe n points and m lines and so forth, and you want to know how they interact. So you also care about incidences. I should say these are finite configurations. Okay, so for example, you might care about an incidence between a point and a line, and an incidence is defined to be a pair, a point P and a line L, where the point P lies on the line L. Okay, and so on and so forth. And these guys can live maybe in a Euclidean space or over some other field, or you could put them in other varieties or whatever. Okay, and you're interested in just sort of counting how many points and lines and planes and so forth you can have. So typical questions in this you could ask, for example, so some problems. So just some sample problems. One is incidences in the plane. So given n points and m lines in the plane, R2, Euclidean plane, how many incidences? Between these points and lines can one have? Okay. Okay, so given 10 points and 10 lines, how many pairs of points and lines can you have such that the point lies on the line? Okay, so let's call this number I. So of course there's a trivial bound of n times m, because there's only n points and m lines, but you can't really attain that bound because it's not possible even once you get to, I think, to 3 points and 3 lines to have all lines go through all points, because of Euclid's axioms, 2 lines determine at most 1 point, 2 points determine at most 1 line. So this is not the right bound. I mean, it's true, but it's not the sharp bound. What is the yes. Okay. When I say n points, I mean n distinct points. Okay. Cardinality. Okay. No, it's not a scheme or anything. Okay. So all right. Okay. So that's one question. Another question is the finite field Kekera problem. Okay, so now we work in a finite field. Okay, the finite field. Okay, and you pick some dimension d, and you define a Kekera set. Is a subset E of this finite geometry K to the D, which contains a line in every direction. Okay, so you have your finite geometry. Okay, and in every direction you pick some line. Okay, and you take all those lines together, and this will give you a Kekaya set. And the question is, how small can a Kekaya set be? Okay, if you have all lines in every direction, what's the smallest? And you're allowed to slide the lines around. The directions are fixed, but the positions are mobile. Can you slide them around to compress them into a small set? And generally, we're interested in the case where D, you should think of as bounded, dimension bounded, and the field is large, like for example, FP for P large. That's the case that is most interesting applications. This problem was motivated by a problem in Euclidean space, where instead of points and lines in a finite field geometry, you have you replace lines by tubes in Euclidean space. So there's something called the Euclidean Kekaya problem, which has connections to harmonic analysis and PDE, which is still not solved, but I won't talk about that problem today. There's been some partial progress on that actually using the algebraic method, but I think I won't have time to talk about that. Okay, that's two problems. That's the third problem is the joints problem, posed by Shavir. So now we're in R3. Okay, define a joint to be three lines intersecting at a common point that are not coplanar. Okay, so three lines that are not in a common plane, we call it a joint. And the question is, given n lines, how many joints can there be? Okay, so all right. So of course, of course you can have zero joints if the lines don't meet each other. But okay, but the question is, how many can you have? So this is a simple example of a grid. If you take a grid of a cube of points of size about n to the 1/3. If you pick an n to the 1/3 by n to the 1/3 by n to the 1/3 grid of, say, integer lattice points, okay, not n to the 1/3, sorry, n to the 1/2. Okay, then you can make n vertical lines, n horizontal lines, and n horizontal lines in the other direction. Okay, so maybe I have to divide by 3 or something. Okay, so okay, and with 3 vertical lines, horizontal lines, and in each of the coordinate axes, and it will give you about n to the 3/2 joints. Okay, because every point in this grid has got a form a joint. Okay, and so this is a pretty good example. Has a lot of joints, and the question is, can you make any more? Again, this question actually has Euclidean analogs that are quite interesting as well, which I won't discuss here. The fact that you want have this non-degeneracy assumption is important. If you allow lines to be coplanar, then you can have a lot more joints. So I could take an n by n grid, would be n over 10 by n by 10 grid in the plane, and then I can have n over 10 lines going this way, n over 10 lines going this way, and say n over 10 lines in the diagonal direction. And so I can get up to n squared degenerate joints where things are coplanar. But I'm excluding that. I don't consider coplanar triples of lines to be joints. I only consider non-coplanar ones to be joints. So how many joints can there be? Okay, so this is the joints problem. Actually, I think I didn't quite state this correctly. I'm sorry. A joint is actually not the 3 lines. A joint is the common point. Sorry, this is not correct. The joint to be a point incident to 3 non-coplanar lines. Yeah, so it's almost the same definition. I just messed it up a little bit. So like if you have many points, many lines going through one point, that's just one joint. That's not many joints. I think I gave a slightly wrong definition. Yeah. Otherwise, of course, you can get an n cubed joint by having just n points. N lines go for one single point. Okay, so the joints problem, and the last problem I want to mention is the Erdős distance problem. Okay, so given n points in R2, how many distinct distances do they form? Or can they form? Or must they form, sorry. Okay, so, given, if you have 2 points xi, yi, and xj, yj, you can make you form the Euclidean distance, which is just the usual thing. Okay, and so if you have n points, you have n choose 2, so roughly n squared numbers, which are of this type. And so, of course, generically, if you just pick n random points, you'll get about n squared distances. But the question is, can you arrange your set to have many fewer distances? So, for example, if you have 3 points, you can put them in an equilateral triangle, and then you only have one distance. If you have 4 points, though, you can't do that anymore. You have to create at least 2 distances. And the question is, what's the least number of distances you can make for any given, if you have n points? What is the optimal configuration? So, for instance, you could arrange all the n points in arithmetic progression, and that will generate about n distinct distances. That's one example. Slightly more efficient, if you have a grid, an integer grid of size root n by root n, let's say n is a perfect square, then you can do a bit of number theory, and you can count how many distances are on this grid. It turns out to be just a little bit smaller, of the order of n over root log n. Basically, just because not every number is sum of 2 squares, you get a slight saving. And it's conjectured that this is the best possible configuration. And it's almost known, it's not quite known. Okay, so these are typical problems in incidence geometry. And so people have been working on these sort of problems for a long time. And until recently, they were using mostly combinatorial techniques. So the type of methods you use. So you can do very sort of basic things. You just use facts about incidence geometry, sort of obvious things. For example, 2 points, any 2 points determine a line. Okay. So given any 2 points, it's at most one line connecting them. Just even using simple things like that, you can already, for example, start improving upon this utterly trivial bound for the incidence problem between points and lines. You can improve this to, I think in this case, n at 1/2 plus m. You get a slight improvement if you use the fact that 2 points determine a line. If you use the fact that 2 lines determine a point, you get the dual bound. You just combine this with a simple Cauchy-Schwarz argument, which I won't do here. But you can get some bounds, which in some cases give you good results, but usually they don't give you the best possible result. So, for example, Erdős in his paper in 1960 something, he used the fact that any 2 circles intersect at most 2 points, right? Basic fact. And if you just use that fact, you can quickly get a bound that the number of distances has to be at least a constant times root n. This is not very hard. In fact, I could even give you the proof. The reason is that if there's d distinct distances in your configuration, then given any point in your configuration, all the other points are contained in a union of d distinct circles, because there's only d distinct distances from that point. And then you pick another point, and then your configuration is also contained in at most d distinct circles from the other point. So you have d squared pairs of circles, but any pair of circles only meets in at most 2 points. So there's at most 2d squared plus 2 different points you can have. But there's n points, and so the normal distance has to be basically at least root n. Okay, so that's a very simple example of using a very basic fact of incidence geometry, which if you like is sort of level 0 algebraic geometry, to do something. Okay, but but as you can see, you don't get sharp results. You want something of order n, and here I give a bunch like root n. Okay, so typically these bounds don't work directly, but what you can do sometimes, especially if you're working over R. Yeah, so you'll notice that some of these problems are phrased over pretty arbitrary fields. Oh yeah, so the joints problem, actually, I should have said. Sorry. You don't have to phrase it over R. You can phrase it over an arbitrary field. That's exactly the same problem. You could also phrase the line incidence problem and the distance problem over arbitrary fields, but it turns out that if you do so, the problems become kind of trivial. For example, there's this Erdős bound of root n is true in every field because the fact that two circles meet those 2 points is true in every field. But okay, it's not sharp in the case of Euclidean space. But if you replace Euclidean space by a finite field geometry, let's say fp squared, okay, you take a finite field geometry, then root n is the right answer because you can just take actually your set of points to be all of fp squared. Okay, so here there's p squared points in the plane. How many distances do you have? Well, you work in the finite field. There's only p different distances. You figure out the square root. Yeah, okay. If you don't care about the square root, there's only p different values that this can take. So you have p squared points determining p values. And so the Erdős bound is sharp in this case. So if you want to actually solve these Euclidean problems, yes, and there's a similar thing for the point line instance problem showing that the trivial bounds here are also sharp in the finite field case. So, but if you want to go beyond that, you must use something about R that is not true for general fields. You have to use something beyond just algebraic geometry, which you can almost define as things that are true over every field. Well, at least the naive algebraic geometry. So there are other methods that you can use that specifically exploit the structure of R. One method, for example, is the method of crossing numbers. Okay, so if you have a graph is a bunch of edges and vertices and edges connected to each other. Okay, you know that some graphs are planar and some graphs are not. Okay, so this graph actually is planar because I can draw it to be planar, but you know K5 is not planar, and we even know exactly which graphs are planar, which ones are not. But generally, the more edges you have, if you have n vertices, the more edges you have, the less planar you will become. And you can measure how non-planar a graph is by defining what's called the crossing number. So the crossing number of a graph is the least number of crossings that you're forced to have if you try to draw the graph in a plane. So a planar graph has crossing number 0 because you can draw it without. So this graph has crossing number 0. Here I've drawn it with 5 crossings, but if I'm a little bit more clever, I can reduce the number of crossings to. Well, okay. I think I got 1 crossing. Okay, so K5 has a crossing number of 1. And there's something called the crossing number inequality. Yeah, so it turns out that if the number of edges is bigger than 6 times the number of vertices, then you have to have at least 1 crossing. And this is actually ultimately a consequence of Euler's formula. Nice little exercise. So that you have to have at least 1 crossing. Okay, and in fact, there's actually a more precise bound. The crossing number is always bounded by a constant. When e is big enough, it's bounded by a constant times, I think, e squared over n, e cubed over n squared. There's a nice little argument, which I won't give here, that gives some bound on how much a graph must cross itself. Okay, if it is drawn in R2, and this is very useful. It can be used, for example, to give the right bound for this instance problem. So it turns out that the correct bound is actually a constant times n to the 2/3 plus some lower order terms. This is actually the right bound, and we know it's completely sharp except for the constant. And the quickest way to prove this bound is you just take all these lines and points, and you think of this as a graph where the points are the vertices, and the lines, the edges are the line segments between points that are incident to the same line. And there will be a few crossings because, of course, any 2 lines can cross each other, but they can only cross each other once. So this is a graph which is almost planar. There's not very many crossings. And you can use that and the crossing number inequality to tell you that there's not very many edges, which ultimately, if you work it out, tells you there's not very many incidences. And if you put it all together, you get the right bound. So this is a very elegant argument of Park, I think. All right. This is not the first proof of this theorem. This theorem is called the Zermody-Trotter theorem. It was proven back in the 70s. They did not use crossing numbers initially. They used another technique, which is called cell decomposition. And so, by the way, I just want to point out this is because we use Euler's formula, this is something which is very special to R2. Right? There's nothing like this for finite fields. Right? You can't even define the notion of a crossing number in finite fields. So another technique that was used until several, is cell decomposition, and it's the way I view it. It's a method for taking a lousy inequality, a lousy bound for your problem, and hopefully upgrading it to a better bound. And the way it works is that you have some configuration in the let's say in the plane points and lines. You have some points and lines, and you want to count incidences. Okay, and if you just naively use some incidence geometry factor, you get some lousy bound, which is not what you want. But you can often improve the bound that you start with if you can somehow divide your configuration into clusters which are smaller and which don't interact with each other very much. So you want clusters where which are disjoint, so each point only lies in one cluster, and you also want each line to only meet a few of the clusters. Okay. Ideally you would like complete decoupling where all the lines that talk to one cluster don't talk to another cluster, but that's not reasonable. But you can hope to have some limitation as to how many lines can how many clusters a single line can meet. And if you can efficiently divide your big problem into these cells where there are fewer lines and fewer points in each cell, then you can hope to apply, say, your lousy bound to each cell, add it up, and if you're lucky, you get a bound that was better than the bound you started with. And so this is actually a surprisingly powerful technique. You can use this to give, and this is basically Zermody-Trotter's original proof, actually, of this argument, this type of idea. So that's another way to prove this. Now, how can you make these cells? One way to do it is to take some of these lines that in your configuration, pick them at random, say, and you just use them, just like slicing a cake, and then to slice your plane into polygonal regions. So if you pick R lines at, generically, you will slice the plane into about R squared regions. Right? It's a classic high school problem. How many regions do you get in general? So there are R squared regions here, and each line that was not already chosen, each other line can only meet about R of these R squared regions, because it can only meet only cross on the boundaries R times. So this is this is one basic idea you can use. You just create some random lines, divide things into points, into cells, and the lines automatically can only talk to a few of the cells. Now, this doesn't completely trivialize the problem because there's one thing you have to watch out for, is that it could be that all the other points are all lying in one cell. This partition may be trivial in which most of the cells are empty, and in that case you don't actually get any improvement over the bound you started with. So you have to make sure that you do a decomposition that somehow splits up your points sort of fairly evenly among all the cells. And this is the main technical problem with the cell method. So anyway, these are the type of techniques that were used until about 2 years ago to make partial progress on all these problems. So for all these problems, there are various partial results, like this root n, so there's a whole series of results improving this n.5 to n to 2/3, n to the 4/5, and so on and so forth, but not getting really close to the sharpest bound. And similarly for these other problems, you can use these sort of methods. But until recently, then we started using the algebraic geometry method, polynomial method. Oh wow, okay, I'm really burning through the time. Okay, so what's going on here is that we have all these geometric objects. We have like points, and we have lines, and we have like incidences between points and lines. If you like, you can do an isolated diagram here. Incidences project out to the points and the lines. and you're trying to control the how does the cardinality of the points and the cardinality of the lines control the cardinality of the incidences? These are the questions that we care about. And so the idea of the polynomial method is, rather than look at each of all these configurations and try to study how they talk to each other, you introduce a new object. You introduce some algebraic set, such as the zero set of a polynomial. Okay, so some algebraic set of variety. Well, except it doesn't have to be irreducible, but you can think of it as a variety. And you try to choose. So you choose an algebraic set in such a way that it somehow communicates in some way with all of your other structures, your points, your lines, your incidences. And in particular, in such a way that the cardinality of these points, lines, and incidences is somehow connected to the degree of this algebraic set. That the combinatorial complexity of your configurations should somehow be related to the algebraic complexity of this set. And then you can start trying to go through this algebraic set to prove bounds, that you have your points and lines, they control somehow the degree of your set, of your algebraic set, and then you somehow use that to control the degree of incidences. And to go back and forth, you have to start using some algebraic geometry. So, so how does this work? So in its simplest form, it's just, it's just the observation that given a bunch of points in space, you can find a curve or line going through them, and if you don't have too many points, you can choose a fairly simple curve or line that goes through them. So in the plane, for instance, in the plane given any 2 points in the plane, of course we can find a line, a degree 1 curve that goes through any 2 points in the plane. If you have any 3 points, then you can find a circle, which may be degenerate if they're collinear, but you can always find a circle. If you have 5 points, you can always find a conic section that goes through these points, and so on and so forth. So, by the way, why can you always find a conic section through 5 points? This is actually a triviality. If you have 5 points, what is a conic section? Conic section is the locus of a polynomial of this form, of degree at most 2. And so there are 6 degrees of freedom in this polynomial. You can choose 6 different numbers here. Okay, and if you want this polynomial to vanish to vanish at this point, that's one constraint, one linear constraint between these 6 numbers. So if you want your polynomial to vanish at 5 points, that's 5 linear constraints and 6 unknowns. And 6 is bigger than 5, so there is a non-trivial solution to this problem by linear algebra. Hence, there is at least one conic, that conic section that goes through these 5 points. Okay, that's the same reason why there's always a line between 2 points and so forth. And you can find that there's always a degree 3 curve going through 9 points and so on and so forth. And so more generally, just a basic fact, through n points in KD, one can always find a hypersurface degree about n with 1 over d. Okay, so you should think of d as fixed, as bounded, and n is large. This is the case we really care about. Okay, so if you have n points in the plane, you can find a hypersurface of a degree about n squared, or n to the 1/2, sorry, square root n that goes through. And this is very easy to show. It's just that for any degree d, you count how many polynomials of degree less than d there are, and it's about d to the dimension. And so the moment that's bigger than n, you have more unknowns than constraints. And this argument I said before gives you at least one polynomial. Okay, so yeah, so given n points in the plane, I can find some curve of reasonable degree about root n that goes through ortho points. It may not be connected or irreducible, but okay, but I can at least but I can find one. Okay, so that's sort of the first place you get started. That connects points at least with the algebraic set, and then you have to connect things with everything else. So let me give you an example of how this works. So what happened to my PK problem? Here it is. Yeah, so this problem has essentially been solved now from the work of Via from a few years back. So remember we had this Kakea set, the subset of k to the d, and so what he showed was that there's a bound that E is bigger than a constant depending on D times k to the D. That basically it is not possible to have a really small set, Kakaia set. Kakaia sets always have sort of positive density inside the whole space. And we even pretty much know what the CD is. Well, we've got good bounds. I think it's 2 minus D. But okay, but for any fixed dimension, this is a very good bound. So there was a lot of work previously on this sort of problem. Actually, I spent several years working on this problem, and now I can give you a proof in 10 minutes. It's really quite embarrassing, actually, but it just sort of shows you the power of the algebraic method. Actually, this fact, I mean, it's a nice little result, but actually has applications in computer science to randomness extraction, how to generate good random number generators from lousy random number generators, but that's another story. Yeah, so how does this work? So, okay, so you have this Kakaia set. It's a set that has a line in every direction. So it's some funny set E. Okay, it's living inside K of D. And you want to show the set E is large. So we argue by contradiction. Suppose E is small. Suppose E is really quite small. So we just write little of K to the D. So I just mean like really, really small, like less than a small multiple of K to the D. Let me not be too precise about what this means. Okay, so we have this funny set. It's got a line in every direction. We apply our basic fact, okay? And so we know that there is a hypersurface. Okay, so the set E is contained inside a hypersurface and its degree is at most E to 1 over D. So it's smaller, in particular, it's smaller than the size of the field if E is small. Okay, so it's the degree can be somewhat big, but it is not as big as the degree of the whole field. Okay. On the other hand, you have these lines. Okay, now this Kakaia set contains a line in every direction. So this line meets the surface, intersects the surface about k times. So each one of these lines intersects the surface at least k times. Okay, just because by hypothesis E contains the k points of this line in every direction. Okay, and so but on the other hand, this has degree less than k, and so by Bezout's theorem, this is not actually possible unless L is actually completely contained inside this polynomial, this surface. So this line actually has to be contained geometrically inside the surface. Okay, so not just the k points, but the entire line is inside this algebraic surface. So in particular, now what you do is that you extend things to the projective space. You embed this affine space projectively into P, into the projective space, and you go to the hyperplane at infinity. And because the line, yeah, so of course this hypersurface extends to some hypersurface over here on the boundary, and this line also extends to some point at okay, and in fact the point at infinity is just the direction of the line. Okay, and so what you conclude is that at the plane infinity, I don't know what you call it, at the plane infinity, because your Kakaia set contains a line in every direction, this guy contains every direction. In KD. So this, okay. And how many directions are there? There's about k to the d minus 1 of them. Okay. So there's a hypersurface on the plane at infinity which contains a lot of k points. Okay. But on the other hand, you have a basic bound, the Schwarz-Zippel bound, which says that if you have a hypersurface on this hyperplane, this is a d minus 1 dimensional surface, the number of k points that you can have on a hypersurface is just k to the d minus 2 times the degree of P, up to some constant on the plane of infinity. Okay, that's a Schwarz-Zippel bound because every line can contain at most a degree number of points, every generic line, and then so you just And but the degree of p is a lot less than k, and these two facts are contradiction. And so that's it. That's the proof, actually. I mean, it's yeah. I spent 5 years on that problem. Okay. Yeah. So, but this is an example of the polynomial method. Yeah, so this particular example used very little algebraic geometry. Okay, basically linear algebra and Bezout's theorem, not even Bezout's theorem, just a very baby version of Bezout's theorem. Oh, and the fact that you know about the plane infinity. Okay, but so that was one of the simplest examples. Now I'll show you the joints problem. Yeah, so this conjecture is now true. Is now known to be true, that the number of joints is at most in the 3 halves, that this grid example is the best that you can do. And yeah, again, people, well, this time I didn't work on this problem, but many people worked for years on this problem. Actually, no, I did work on this problem, actually. Got a partial result. And yeah, like everybody else, until a year ago, Guth and Katz actually, I think, no, this one was actually 09. Solve this problem. So it's a very similar argument. So there's several ways to phrase it. You can you can start with this fact again, but you can also use a slight variant of this fact. So I said that given through any n points in space, you can find a hypersurface of degree n1 over d. There's a slight variant of this. If you don't start with points, you start with lines, and then you want a hypersurface that contains all these lines. You can do that as well. The only difference is that the exponent changes a little bit. It's the same argument. You look at all polynomials with degree. You ask what it means to vanish on each line, and that's a certain number of constraints, linear constraints on your coefficients, and you can just count your way through, and you get a bound like that. Okay. So anyway, if you accept that fact, so in particular, given n lines in 3 space, there is a degree, there is a hypersurface, not just a surface now, containing these lines. Degree root n. Okay, just from this, it's basically an algebra fact. So you've got all these lines, okay, and so they're contained inside some hypersurface of this degree. Okay, so for example, in this grid example, this root n by root n by root n grid, the relevant hypersurface is just n to 1/2 horizontal planes, n to 1/2 vertical planes, and 1/2 more vertical planes. Okay, so it's not an irreducible hypersurface, but it is a hypersurface. Okay, so these are so you have this hypersurface. Okay, now your hypersurface has got smooth points and non-smooth points. Okay, so a smooth point is where you have a tangent space, and a non-smooth point is where you don't have a tangent space. If you're at a smooth point, you can't have a joint, because by definition, the joints have to be coplanar and non-coplanar. And if you have a tangent space, you can't have that. Okay, remember, the lines lie in the surface. So the lines don't just lie in the surface; they actually lie in the singular points of a surface. So cheating a little bit, that's basically not just the set where the polynomial vanishes, but also the polynomial to second order vanishes. So in fact, you're not actually just contained in a degree root n hypersurface. You're actually contained in a degree n curve. Okay, but it's a degree n curve that's formed basically by intersecting degree root n hypersurfaces. It's a special type of degree n curve. So all the joints must actually lie in this curve. Now, the lines don't have to lie in this curve. The lines, remember, all the lines lie in this surface. The joints must lie in this curve, but the lines could still could still just lie in the surface and not in the curve. But if the lines do not lie in the curve, then they can only meet this curve in at most root n points, because this curve came from intersecting degree root n hypersurfaces together. And so in that case, there are n lines. If they can only meet root n joints each, that's at most n to the 3/2 joints. Okay, so that's okay. So the lines that don't lie in the surface are fine. And so all the lines must lie in the surface as well. You can throw out all the lines that don't lie in the surface. Okay. But then you can repeat the same argument. This curve has got smooth points and singular points. If you're smooth, again, because your tangent space is too small, it can't support a joint. And so you must actually be stuck inside a zero-dimensional, the singular points of this curve, which is now a zero-dimensional set. And now it's not actually possible for the lines to be contained inside this set at all, because the dimension is too small. And so now each line can only meet at most root end joints again. And so and then again you get this bound. So I skipped over a few details, but you can see that you didn't use very much. I mean, you used a little bit more algebraic geometry. Now you know about singular points and smooth points, but still, it's very simple.
I missed something. Did you say the singular points of the surface form the degree n curve?
Yeah. Well, it's the intersection of two polynomials of two surfaces of degree root n. It's the way P and its derivatives vanish.
Why there's many derivatives?
Okay.
All the derivatives?
Yeah, all the first derivatives. Okay, so it's contained inside a curve of this degree. Well, okay. Well, I don't actually.
So it's contained in p equals 0 and dp by dx equals 0, for instance.
Yes.
So you have a bound.
Yes.
Yes.
Okay. Yeah, and yeah, you can assume that p is say square free or something to begin with. Yeah. All right. Yeah. Yeah. So there were some technical details I was glossing over, but yeah, this is the sketch of the argument. Okay, and this argument, by the way, works in any field. Right? I didn't use anything but R in that argument. Okay, so yeah, so that solves, for example, the finite fluid problem and the joints problem. For the other problems I mentioned, symmetry trotter and this distance problem, as I said before, those results, those problems, they have to use something special about R. So you can't just use algebraic geometry to solve these problems, because that would work of any field, and we know that there's something special about R. So there's this extra trick. So yeah, so we have the general fact which is true over any field, which is that if you have n points, you can find a reasonable hypersurface of some reasonably controlled degree that goes through all of them. But in RD, there's you can do more. That fact's still true. But if you don't like the fact that this degree is so high, yeah, if you have to connect every single point, then you basically have to have this degree, right? Just some degrees of freedom. But if you're happy to just capture some of the points and leave other points behind, you can get by with a lot smaller degree. And well, let me try to explain what I'm saying. So I told you before that given any 2 points, I can make a line, and then between every 5 points, I can put a conic section. So in R, there's a generalization of this fact. So this is very simple. It's just linear algebra. But there is a generalization of this fact called the ham sandwich theorem. That if you have instead of 2 points, you have 2 bodies, 2 open sets, say, open bounded sets. I can always find a line that goes through these sets, but not only that, it bisects these into 2 sets of equal area. Okay. Now, if I have 5 sets, okay, and this is very easy, and then you have similar things in higher dimensions, and it follows from the Borsuk-Ulam theorem, which is almost it's basic algebraic topology. Now, if you have 5 sets, then I can't bisect all 5 of them using a single line. But I can bisect all 5 of them using a single conic. Okay, that there will exist a conic, okay, that bisects all of these. And the proof is almost the same as the proof that that there's a conic that goes through 5 points. This is like a limiting case of this fact. So here, what you did is that you look at all the possible quadratic polynomials as a dimension 6 space, and by linear algebra, one of them had to vanish on all 5 of these points. So here you look at the space of all quadratic polynomials as again a 6-dimensional space. For each of those polynomials, you measure the imbalance, the area on one side of the polynomial minus the area of the other side, and it gives you this element of R5. You have a map from R6 to R5, which is odd. If you P of minus P, it flips the sign. And the Borsuk-Ulam theorem tells you that such a point there must be a zero of such a point, and that's the, okay. And so yeah, so there's a version of this fact which is the polynomial Ham-Sandwich theorem. Okay. Through n bodies in, okay, and this is the fact that only works in Euclidean space. Okay, it doesn't even make sense, this bisection in say over a finite field. Given n bodies in RD, there is a polynomial. Well, there's a hypersurface. Degree n1 over d that bisects all the bodies. Okay, so just like this picture. Okay, so it's a more general form of, so this fact, well, before the points, is just the limiting case when the bodies just shrink to a single point each. Now, this particular fact is not so useful for these instance geometry problems as stated, because it involves open bodies, and these are configurations of finite points. But you can take a limiting case where each of these bodies, they don't be connected. I can take the bodies to be, for example, each body can be a union of small balls around little points, and then you can shrink the radius of these points to 0. And so there's a limiting version of this theorem involving just sets of discrete points. So rather than n bodies, you can have n discrete points, n finite sets. So you have some set S1, some set S2 of points, and so forth. And you can, and by taking a limit from this of this fact, and using the fact that space of all polynomials is compact in projectively, you get a discrete version. Given n different families of sets, finite sets, you can find a hypersurface of this degree, which will pass through some of these points, but it will bisect all the others into equal cardinalities. It will cut them exactly into half. Okay, that's just a limiting case of this continuous theorem. And again, this is something that's only true in Euclidean space. Again, bisection doesn't even make sense because if you don't have an order on your field. Actually, one amusing thing is that this statement is true for all ordered fields, just from the Tarski-Seidenberg theorem, but it's you can't prove it other than transferring to R first and then using topology. It's kind of a weird thing. Anyway, okay, but all right. So you can use this to get. This leads to a very good cell decomposition. And so one corollary is that given n points, in Euclidean space and a degree d, you can find a hypersurface of degree about d that partitions Rd into a certain number of cells, but about d to the d cells, turns out, each of which has about n over d to the d points. So there's a way to equitably cut up a large configuration of points, no matter how they're distributed, into basically equally sized smaller configurations of points using a curve that's not too high a degree. So I'll just draw a picture maybe to illustrate what's going on. So if I have n points, then it's very easy to find a line through these n points which will contain some of these points, but on one side there'll be at most n over 2 points on this side and at most n over 2 points on this side. I can find a line that bisects, bisects here. In fact, and once I do that, I can actually even find a second line from the Ham-Sandwich theorem, in fact, from the linear Ham-Sandwich theorem, that bisects those two cells that are created. Now I have 4 cells, each of which have n over 4 points. Okay. Now at this point, I can't use lines anymore, but if I use the polynomial Ham-Sandwich theorem, I can find a conic section, which will bisect what's left into 8 cells, each of which have size of about n over 8 points. And you can continue this, and if you just keep track of all the degrees, you get this particular fact. And so what you can do is that you can start with a large configuration of points and turn them into a whole collection of smaller configurations of points, with much smaller size, and with a good bound on the degree. And that's important because once you have that degree bound, that means that all the lines, if you're counting, say, 0.9 incidences, any line that has to meet this hypersurface can only meet, so there's d to the d cells, but they can only meet about d of the cells, because a line can only meet a degree d hypersurface in at most d points. So each of these lines only meets a small fraction of these cells, and so these cells don't really talk to each other very much. And so because of that, you can work on each cell separately, get some bound, and then put it all together and get a better bound, and you get to pick d. And if you pick d correctly, you can often get very sharp bounds. And so this, for example, can be used to give a fairly short proof of this Zermelo-Trotter theorem, which I don't have time to give. And a more sophisticated version of that idea was used by Guth and Katz in 2010. I should also mention, so this gives you Zermelo-Trotter theorem in R2 just this week, actually. Joseph Solomushi and I managed to also get the same result in C2 by this sort of method. That was a previous result. It was first obtained by Toth by a much more complicated method, and we can prove the same bound. Well, not quite, actually. We lose a tiny epsilon here for technical reasons, but essentially it's the same bound in the complex plane too, C2. Okay, I mean, the Hammond symmetry doesn't directly work in C2. It doesn't quite make sense, but you can think of C2 as R4, and that turns out to sort of work after a little bit of extra effort. But so I'm almost out of time. So the last thing is this distance problem. So unfortunately, I don't have time to explain how it works exactly. But there's this ingenious way to transform the distance problem, which is a problem about points in the plane, to an incidence problem. Pushing points and lines in R3. Maybe I'll try to very, very briefly say why there's a connection. See, if you have a bunch of points in the plane, and if you have very few distances, if the distances are repeated many, many times, then you must get a lot of congruent line segments. That there must be a lot of pairs A, B, C, D, where AB is congruent to CD. Okay? And if AB is congruent to CD, then it's obvious that there's a rigid motion. There exists some rigid motion in the space of all rigid motions of the plane that maps this line segment to this line segment. And this is a three-dimensional space. It's essentially R3. It's R3 with you glue on some stuff on the end, but it's essentially R3. And this is actually a unique. There's actually a unique rigid motion, orientation-preserving rigid motion that maps this line segment to this line segment. And so what you can do is that you can work now in the space of rigid motions of the plane, which is locally R3, and you have all these rigid motions, which you think of now as points. And on the other hand, given any 2 points A and C, you can ask for the stabilizer, the relative stabilizer, the set of all rigid motions that map A to C. And that's a one-dimensional set of rotations. Okay, you can translate A to C, and then you can rotate in a one-dimensional set. And there's this minor miracle that if you choose the right coordinate system, those stabilizers are actually lines. It's a nice little. The degree is low enough that you can just sort of make this work. And so this rotation is actually So given the points A and C, there's this line of rigid motions. It's all the rigid motions that map A to C. And there's a line from B to there's a line of rigid motions that map B to D. And this rigid motion is just the intersection of these two. So it's a little bit like a joint, except that there's only 2 lines rather than 3 lines. But it's kind of like a joint. And so you can relate the problem of bounding distances to the problem of counting, not quite joints, but sort of this weaker version of a joint in point-line configurations in space. And so you can set up the same machinery. So I gave you a very quick proof of the joints conjecture. And it relied on the fact that if you had a smooth point on a hypersurface, on a surface, you can't have 3 lines that are non-coplanar. Now, unfortunately, on a surface, you can have 2 lines that are non-coplanar. Well, sorry, no. You can have 2 lines. Okay. So you have to work a little harder because you only have 2 lines instead of 3. Okay. But the key point now is that so you have to use a little bit more algebraic geometry. So the extra stuff you use is that if you have a surface in K3 even, if you have a surface, it is possible, so it's completely possible to have a point in the surface and have two non-parallel lines go through, two different lines go through that point in the surface. It's completely possible. But most surfaces don't have many lines on them. Okay, if you consider, say, irreducible surfaces, there's only you can classify irreducible surfaces into 3 types. There's the singly ruled surfaces, which have a single ruling. Okay, there's the doubly ruled surfaces, which have a double ruling. And then there are the non-ruled surfaces. Okay, let's say we have a surface of degree D. Okay, so if you have a non-ruled surface, then you don't have any families of lines, but you can still have the occasional odd line that's not part of a family lying in the set. But it turns out that if you have a degree D curve, surface, you can't have that many lines. These guys, there's a bound on how many lines they have. In fact, there's only D squared lines that you can have in a surface of degree D. It's basically a Bezout theorem type thing. Basically, you can the subvariety. I mean, the set of, you can take all these lines and take their union, put them all together. That's another algebraic set, which is formed from the polynomial p and its derivatives. You can write it in terms of p and its derivatives, and so it has degree D squared at most. Similarly, if you have a singly ruled surface, then there's one ruling, and then there's a couple. You can still have a couple lines not in that ruling, but again, you can only have D squared exceptional lines not in that ruling. And if you have and you have a pair of lines, only one of them can be in this ruling, unless you're on a singular point of the ruling, but you can deal with that case separately. So those cases you can deal with. And finally, you have the doubly ruled surfaces, which look bad, because these guys do have a lot of points where you have 2 lines going through that point, like almost a generic point does that. But these are very rare, and in particular, they're classified. In K3, the only doubly ruled surfaces are the plane and the quadratic surfaces. You have to go to degree at most 2. You can't have high degree surfaces that are doubly ruled. So that's this algebraic geometry fact. And so you get this big saving in degree, and you can use that as well. So, okay, putting it all together is a little bit complicated, and I definitely do not have time to do it all. But you can begin to see that you have to use just a little bit of actual knowledge of algebraic geometry to proceed at this point. Such as the classification of doubly ruled surfaces. But there are still many problems out there that we'd like to solve, especially in higher dimensions, where you have to start dealing with much higher degree things than surfaces and lines, and there we probably will have to need some more high-powered algebraic geometry to proceed. So it's an interesting new area. So there's still lots of developments, but it's just getting started. Anyway, that's it. Thank you very much.
Any questions?
What are the sort of main high-dimensional open problems that you think might be subtools or algebraic?
Well, I think you just have to try it and see. So we don't yet, I mean, these techniques are very new. Well, the polynomial method has been used in other contexts, like in additive combinatorics, for example, for many years. And for instance geometry, it's only 2 or 3 years last year we've been using them. So I don't think anyone has a really good sense of which problems are easily susceptible to this and which ones are not. I mean, clearly you want some algebraic structure, right? But apart from that, it's, and I think for almost any of these problems, you can always apply this method and get something, but it may not be the best bound. I mean, it's rather remarkable that in each of the cases I mentioned, you actually get the sharp bound, and which is a very promising sign, but that may not be the truth in general. So I'm working actually with Joseph and my former student, my current student actually, and Jordan Ellenberg on looking at the Erdős distance problem in 3 dimensions, for example. We haven't yet solve the problem, but maybe it's amenable. Yeah, but the algebraic geometry gets significantly more interesting.
Any other questions? If not, we thank Terry again for a wonderful talk.